Okay, first question that you can have a look at is page 1. Okay, just have a look at page 1 of your ideal gas worksheet. This one is June 15 P42. So here, they mentioned to you this particular thing, right? You have a sample of gas at room temperature, 5 atoms at the following speeds. For these 5 atoms, calculate to 3 significant figures, your mean speed. So right now, if you want to find out your mean speed, you just take C1 plus C2 plus C3 plus C4 plus C5 divided by N. So your expression will just be something like this. Okay. And I know that I have some power of 3 here, 10 power 3 here. I can actually just factorize them out first when I add up those speeds. Okay. So eventually your mean speed is just going to be 1.44 times 10 power 3. Okay. Then the next part here is asking you for your mean square speed. Mean square speed can be thought of as you squaring all the speeds and then adding them up. So it's C1 square plus C2 square plus C3 square plus C4 square plus C5 square before dividing it by N. This is how you find your mean square speed. You need to square all the speeds before adding them up and then divide by the number of speeds that you have. Okay, so same thing again. You have the 10 power 3 here. You can just factorize it out, but make sure you square it. Okay, eventually your mean square speed will be the same as 2.09 times 10 power 6. Okay, now if you're asked to find mean speed square, which is different from mean square speed, mean speed square is C squared here like this. To find that value, it's actually C1 plus C2 plus C3 plus C4 plus C5 divide by N and then square. So they are not the same. Okay, that's why we told you that mean square speed is not the same as mean speed square. They are different in the way that you calculate them. Okay, so this one, don't ever use something like this. So your mean square speed was 2.09 times 10 power 6. This one, I think you can get it very quickly. And then the next one will be finding out your root mean square speed. So root mean square speed is just the square root of your mean square speed. So the square root that value, you will get the answer is 1.45 times 10 power 3 meter per second. Okay, so this one is pretty straightforward. Okay, then if you're okay with that, then we move on to something a bit more challenging. Next one that you can have a look at is page 5. Have a look at page 5. Page 5 is March 2016 P42. Okay, right. So state what is meant by internal energy. Internal energy is actually the sum of a random distribution of kinetic and potential energies of molecules in a system. This one is something that you've done in the previous chapter. You can just recopy back the definition from your notes. The one that I've written here is actually written slightly differently, but it's actually the same as what you have in the notes. Okay. Now, if you look at part 2, the basic assumption of the kinetic theory of gases that leads to the conclusion that there is zero potential energy between the molecules of an ideal gas. What is the basic assumption there that tells you that? How is it possible I can say that there is zero potential energy between molecules of an ideal gas? The reason why there's zero potential energy between molecules of an ideal gas is because there are no intermolecular forces in the first place, or there are no forces of attraction or repulsion between the molecules. So I think if you just write no intermolecular forces, this is actually the shortest, best answer to write. Okay, so this one is okay. Okay, now move on to part B. Now for part B, the pressure P and volume V of an ideal gas are related by this equation, where you have PV equals to 1 over 3 nmc square, where n is number of molecules, m is the mass of a molecule, and c square is the mean square speed. Use this equation to show that the mean kinetic energy of a molecule is given by this, where K is the Boltzmann constant and T is your thermodynamic temperature. So we've actually just done the derivation from the notes just now. You're always supposed to compare it with PV equals to NKT. This one is your first equation. The second equation is PV equals to NKT. So if you follow the derivation that I did in the notes, you equate 1 and 2, eventually you'll get half mc squared equals to 3 over 2 kt. Now this one is not yet the end. Usually when you reach this part here, you have to follow up with this. You have to specifically write that since Ek is half mc squared, therefore Ek is 3 over 2 kt. Okay? So that's for that particular section here. Right, then if you're okay, I move on to the next one. Next one should be something more relevant to what we've just done. Okay, so move on to the next page. Now, the next part of your question, you have a cylinder that contains 17 grams of oxygen gas at a temperature of 12 degrees Celsius. The mass of 1 mole of oxygen gas is 32 grams. It may be assumed that oxygen behaves as an ideal gas. You assume it's an ideal gas here. Now calculate for the oxygen gas in the cylinder the mean kinetic energy of a molecule. Okay, here they want the mean kinetic energy of a molecule. So the equation that should come to mind is going to be this one. Ek equals to 3 over 2 kt. Okay, so your Boltzmann constant is 1.3 times 10 power minus 23. You will eventually be able to get it from your data sheet. And your temperature here is 12 degrees Celsius. You just change it to Kelvin. I believe I did mention to you guys before that if your temperature is in degrees Celsius and you want to change it to Kelvin, you either just plus 273 or plus 273.15. Plus 273 is from your marking scheme. Plus 273.15 is from your syllabus booklet. Both are acceptable. Just use whichever you like. I have a tendency to use 273.15, but if you just write 273 is fine. Okay. So eventually your Ek is going to be 5.9 times 10 power minus 21 joules. This is the kinetic energy of a molecule. Okay. Now the next one requires you to find out the number of molecules inside your gas right now. Okay. So you consider this now. 1 mole is 32 grams. Or maybe I shift it the other way around. 32 grams of oxygen gas is 1 mole. What if you have 17 grams now? How much would 17 grams give you in terms of number of moles? So from here, you can actually kind of deduce this. Your number of moles is going to be 17 over 32 times 1. This is your number of moles. Okay, number of moles n. And then to find your number of molecules is n over Na, right? Such that number of molecules is your number of moles times your Avogadro constant. So the number of moles, you've already found it from here. Okay, it's 17 divided by 32 times 1. Okay, so number of molecules will give you an answer of 3.2 times 10 power 23 here. Okay, so pretty straightforward for this one. And last question here is asking you about total internal energy, right? So just now we already said that IE is KE plus PE ideal gas has no IMF. It has no intermolecular force, therefore PE is 0. So KE is just, so IE is just KE. Okay. So IE is just KE is 3/2 NKT. This KE here, as I mentioned, must be the total KE of all gas molecules. So to find your KE total, it was N times EK, it was 3/2 NKT, isn't it? So that's how I got this. All right. But here you can actually just use this one only now, because you already found out your EK value from here. Okay. So your internal energy is going to be N times EK. Your number of molecules is 3.2 times 10 power 23. Your kinetic energy of a molecule is 5.9 times 10 power minus 21. Your final answer will be 1.89 times 10 power 3 joules. Okay. So this one here, maybe I should just modify a little. This one is going to be N times EK. It will be 3/2 NKT. Okay. So this is how you would get your answer here. We can probably have a look at page 13, half of page 13. Now you have a cylinder that contains 5.12 moles of an ideal gas at pressure 5 times 10 power 5 pascal and volume of 3.8 times 10 power 4 centimeter cube. Determine the temperature of the gas. So this one is pretty straightforward. You just use PV equals to nRT because you're given information about number of moles. Okay. So in your case, you just sum in your values, 5.6 times 10 power minus 5, 3.8 times 10 power minus 4. Notice that there's a 10 power minus 6 here. It's because you're trying to convert your centimeter cube to meter cube. So how do you know it's 10 power minus 6 is through this way? 1 centimeter cube is the same as 1 centimeter inside a bracket that is cube. 1 centimeter is 10 power minus 2 meter inside that same bracket that is cube, so that you get 10 power minus 6 meter cube. That's why you need to multiply with 10 power minus 6 here. Okay. And then your number of moles is 5.12. Molar gas constant is 8.31. You now can find out your absolute temperature or thermodynamic temperature. It's going to be 500 kelvins. Okay. And then last question in part B. Your average kinetic energy EK of a molecule of the gas is given by this expression. EK equals to 3/2 kT, where K is your Boltzmann constant and T is your thermodynamic temperature. The gas is heated at constant pressure, so this is a keyword. So that its temperature rises by 125 Kelvin. Temperature is rising by 125 Kelvin. This is plus 125 Kelvin. Okay. Use your answer in A to determine the new volume of the gas. So now you can use PV equals to nRT for your case now. Your gas was basically going from state 1 to state 2. For both cases, because it's an ideal gas, PV equals to nRT will still apply. But there are some things that will remain constant. First one being constant pressure here. Second one being that it's a closed system, no gas is added or removed, and or number of moles is constant, and your molar gas constant itself is constant. So you can say that P, N, and R are constant, such that volume is proportional to temperature. So now V2 to V1 is equals to T2 to T1. All right. So V2 will be T2 T1 times T2 over T1 times V1. Your T1 was originally 500 Kelvin. This one was your T1. And then when you're going for the T2, they told you that your temperature rises by 125 Kelvin. T2 is actually T1 plus 125 Kelvin. So it's supposed to be 500 plus 125. That's why you get this expression here for T2. Divide by your T1, multiply with your volume of your gas, you will eventually get your answer as 4.75 times 10 power 4 centimeter cube. Okay. Now notice that your final answer is in centimeter cube. You can just leave your answer here as centimeter cube. You don't need to purposely change it back to meter cube, unlike the ones that you did here. I know I can just leave it there because you see your Kelvin temperature units will cancel off. So whatever you have for V2 would just be forming this unit. Okay. So that one should be it. In the next question, they ask you to calculate the increase in internal energy of the gas and explain your working. Okay, so what is the increase in internal energy of your gas now when your ideal gas was moving from state 1 to state 2? So right now, let's just consider a few things. If you recall, the definition of internal energy is the sum of your kinetic energy plus your potential energy. But since this is an ideal gas currently, they've already mentioned it to you here. You know that ideal gas has no intermolecular force. Ideal gas has no intermolecular force. Therefore, PE is 0. So from here, internal energy of ideal gas is just its kinetic energy, such that any change in its internal energy is really just the change in the kinetic energy of the gas. Okay, and then from there, this one is the change in KE for the whole gas containing all the molecules. So the only thing that you have learned so far that relates to kinetic energy of your gas molecule was this equation here, where they mentioned that EK equals to 3 over 2 KT, which is the same equation that is given to you inside the question now. So this one is relating to the average KE of a single molecule only. Just one single molecule. It doesn't take into account n number of molecules. So here, if you wanted to find out the total KE, the total change in KE, you can think of it as this first. If this one here being the kinetic energy of a gas molecule, you can say that the average change in kinetic energy of a single gas molecule would be 3 over 2k delta T. You're basically just introducing a delta sign here, where you say change in average kinetic energy of a gas molecule is equals to 3 over 2k times change in your temperature. Okay, so this is one part to remember. So right now comes the part where you want to find out your total KE. So your KE total is actually the number of gas molecules you have multiplied with the average kinetic energy of a single gas molecule, such that right now, if you want to find the total change in your KE, it must be number of molecules n multiplied with the change in kinetic energy of a single gas molecule. Okay, so this is one relation that you can roughly deduce out. If you want to find the total change in kinetic energy of your gas, you just take the number of gas molecule multiply with the change in kinetic energy of a single gas molecule. From there, you should be able to then relate it to this first part here, where you then say that the change in kinetic energy is equals to your change in internal energy. Your question is asking you to find the increase in internal energy of the gas, right? So you need to find the change in kinetic energy first. But before that, you need to kind of like explain how do you get to that part. So you could probably say something like this: for an ideal gas, the change in internal energy is equal to the change in total kinetic energy of your gas molecules. So written in equation form, delta U is equals to delta KE. So right now, your change in internal energy is equals to the change in total KE, which in turn is equals to the change in KE of a single gas molecule multiplied with n number of molecules. Okay, so right now, if you're talking about the change in kinetic energy of a single molecule, you can use this equation from before, isn't it? If you're talking about the change in kinetic energy of a single molecule, is 3 over 2k delta T. Okay, so you have 3 over 2k delta T here, multiply with your number of molecules. But before you can go to that, you again need to do something with your number of molecules n here. You remember that number of moles is number of molecule n's divided by your Avogadro constant, such that number of molecules is now number of moles times your Avogadro constant. So right now, rather than putting it as number of molecules, you put it as number of moles multiplied with your Avogadro constant. Because as it is right now, you do not have the number of molecules. You did not find the number of molecules in your question right now. You did not do it in the previous part. So you have to change this to another different form. You can change it to in terms of number of moles and the Avogadro constant. When it comes to the number of moles, you actually do know the number of moles is already stated at the beginning of your question. And then your Avogadro constant is a constant you can get from your data sheet. So no issues there. So from there, just substitute in all the relevant values. The Boltzmann constant, the change in temperature, the number of moles, and the Avogadro constant, you should be able to get the answer as 7.98 times 10 power 3 joules. Okay, your change in temperature is actually this part here. They already mentioned to you that from state 1 to state 2, the temperature actually rose by 125 Kelvin. This is your change in temperature. So you just use that temperature change. Okay, so this is your increase in internal energy. Okay, there's a next part to this question. The next part of the question is asking you to use your answer in B1, the one that you just found, to determine the external work that has been done during the expansion of your gas. Okay, how much work has already been done for your gas right now? Now, if you remember in the earlier part of the question, they did mention one important thing to you. Your gas was heated at constant pressure. Okay, your gas was heated at constant pressure, and there's also a change in volume associated with this. Okay, your volume was originally 3.8 times 10 power 4 centimeter cube. And then right over here in part B, after your gas was heated at constant pressure, you were required to find the new volume, which in turn become 4.75 times 10 power 4. So right now, if you try to write that at one side, V1 was 3.80 times 10 power 4 centimeter cube. Is now changing to V2 equals to 4.75 times 10 power 4 centimeter cube. And this one is occurring at constant pressure, where your volume is increasing. Okay, so if you now want to find out the work done by your gas, you just need to use your equation for work done by gas that you've learned in AS before. So you can actually just say that work done is equals to the pressure times the change in your volume. Pressure here is 5.6 times 10 power 5. You can get it from the earlier part of your question right over here. This first statement here is 5.6 times 10 power 5 Pascal. Then your change in volume is basically just the difference between these two values. So it'll be 4.75 minus 3.8. times 10 power 4. But don't forget to change it from centimeter cube to meter cube, where you need to multiply with 10 power minus 6. Just to recap a little how you change from centimeter cube to meter cube. 1 centimeter cube is the same as 1 centimeter inside a bracket that is cube. 1 centimeter is 10 power minus 2 meter inside the same bracket cube, such that you get 10 power minus 6 meter cube. Okay, that's how you got your conversion here. So multiply everything together, you will get 5.32 times 10 power 3 joules. Okay, this is your final answer. All right. Okay, then if you move on to the second part 2 here, calculate the total thermal energy that has been used to heat up the gas in B. All right. So when you are asked to find thermal energy and whatnot, usually you need to relate to your thermodynamic first law. So thermodynamic first law is written as increase in internal energy is equals to work done on system plus heat supplied to the system, right? And that from this equation, there's a specific meaning when you have a positive and negative to the variables, isn't it? So right now, if you try to find out your thermal energy, the delta Q here, delta Q by right would be delta U minus delta W, okay? But before you sub your values in, just consider a few things. Your case here just now was that you had an increase in internal energy. So your delta U is positive. This one you know because the question says find out the increase in internal energy of the gas. Okay. So your delta Q here is positive. But what about your work done? You see, if you look back at the part above here, from 3.8 to 4.75, this one is actually a volume increase. Okay. So when it comes to volume increase, that means work is done by the system. Therefore, delta W is negative. Okay. So right now, if you want to sub in your values for delta U and delta W, you need to take into account the specific sign that they should have. Your delta U, the increase in internal energy is 7,980. It's going to be positive. You already found this value in part 2 before this. Okay. But when it comes to your work done, this one you need to be careful a bit because your work done is negative here. You already found out the magnitude as 5.32 times 10 power 3. Okay. But when you want to put the value in to your equation for thermodynamic first law, you need to put in negative to it because this is work done by gas. The value is supposed to be negative. Okay. So that right now you have two negative here. They're supposed to add up together. Your final answer would be 13.3 times 10 power 3 joules, just like that. Okay, so this is one part of your ideal gas questions. Right, so if this is okay, then you move on to another question